Okay, so off we go. Let's see here. Where we were last time, we were talking about flux, and just a reminder that. Okay, let's see. I've got to do something about this door. So, just a reminder that flux is something we talked about back in chapter 3. Right? And it gets control of this idea of if you know something about the velocity of the fluid and exactly how you set that up is different in every circumstance. And so let's not get back into the weeds on that. But if you have a vector field representing the flow of the fluid, mostly representing velocity, flux is the thing, this formula right here is the thing that tells you in some appropriate sense how much fluid per unit time is flowing through your surface. Okay, but of course that does have a couple of assumptions. It assumes that your surface is flat. It assumes that your vector field is constant. And for a first time through the material, that's a reasonable assumption to keep it simple. But now we want to talk about. Let's talk about the real world now, where stuff just generally most of the time is not flat, and vector fields are most of the time not constants. Okay, so how to deal? Well, no surprise, I hope. We're going to chop it up into little pieces, solve the problem on each piece, and then add them up, right? That's what we always do in this class. That's how integrals work. It's a big idea behind a Riemann sum. And so when you chop it up into a little piece, you take a curved surface, sure, but on each little piece, it's approximately flat. And on each little piece, if you were to look at the vector field, which is, wildly non-constant, broadly, if you look over, great distances, sure, it's not constant, right? But if you look on the little piece, it's so little, the idea is the vector field just doesn't have much room to change very much. And so it's approximately constant. And so on each little piece, that's an easy problem. On each little piece, this is a chapter 3 style flux question. So you just write it down. And approximately, what we're talking about then is, again, for each little piece of area of size ds, and if you're looking at a vector field that, again, is approximately constant, then that goes there, and we have our usual formula for, the amount of flux that we get from that one little piece computed by the usual formula, vector field dot normal vector times the area. All right, and then how you add that up is exactly what you would think and hope. On each little piece, we have a formula. All right, well, if you want to add up over the entire whole of the surface, cool. You just write that down. Right? We're kind of expecting at some point this is going to, correction. We were expecting to get a scalar surface integral, and it appears that we kind of have. But in fact, we don't really have what I'm going to call a scalar surface integral here. There is a hidden complication here, and that is with this normal vector. So let me go back up to something I glossed over, a little formality. If we are going to talk about flux through a surface, we do have to decide which direction are we talking about, right? Because if I have a surface here and I want to know how much fluid is flowing through the surface, there is a difference between volume per unit time in that direction versus that amount of volume per unit time going the other direction. I need to be able to distinguish between those. Right? And in order to distinguish between those, one's going to be plus and one's going to be minus. Well, I've got to decide which one of those is going to be plus and which one is going to be minus. And we do this by way of what we call an orientation vector. Right? And so when we're computing flux through a surface, in fact, we need a little bit more sophisticated of an object. We need this thing called an oriented surface. A surface, just a surface, just sitting there. I don't know which direction you mean is positive. So we need an oriented surface. All right, so that being the case, notice you come down here, that orientation vector does play a significant role. That's the thing that you dot with. And if you choose to orient this one way, this will be one expression. But if you orient the other way, this is going to point the other direction. This dot product will be the negative of what it would have been. You will get a different answer. So notice that is in our integrand. Right? Orientation. So this integrand, let's see, let me highlight here. This, what I'm going to loosely call integrand here, is not just a function of x, y, and z. This depends on how your surface is oriented. It depends not just on the choice that you've made between the two different possibilities of which way that orientation can go, but how does, no, I'll just use this pen. How does that piece of surface sit in space, right? This is different from that, which is different from that, which is different from that, right? So this is not just dependent on position alone. So I like to think of differentials as talking about the domain, and integrands talking about what you're doing with the domain, what you're doing at different points on the domain, but not really being dependent on the domain. So I like to rewrite, and this is very common, by the way, our book does this as well. These two things, we pair them together and call them the ds vector. And then the vector field that had been part of what we were calling the integrand, now we see is the entire integrand. I think there's a better way to do things, just from a notational standpoint, ultimately from a simplicity and naturality standpoint. If you think about it, everything we need to know about a little piece of surface is wrapped up inside of this, what I'm calling ds vector. Right? You think about what's in the ds vector. That's the orientation of that little piece of surface. Ds scalar is the size of that little piece of surface. Everything you need to know about that little piece of surface is inside of the ds vector. And then the vector field is this completely independent thing that is what it is and is a function of x, y, and z. Okay. All right, now that seems a little bit weird, right? Seems kind of arbitrary. But let me remind you, we've done something like this previously, flashing back to, vector line integrals. We were computing work as an integral where we're adding up little pieces of work. And now how we developed this was a little bit different because it's a different physics application and there's different sort of convenient foots indoors to make calculations easier to kind of develop one way or another way, and that's just context. It doesn't really mean much mathematically. But we have a formula that gives us this. And we had a different formula for work that was this. And recall, it made sense at the time to lump these together as the dx vector. Now again, in fact, we developed it in the other direction. We wrote down the dx vector and then broke that down into these, direction and magnitude, and t being the direction of the velocity implies the orientation, all that business. We kind of did it right to left in some sense. Here, we're doing it left to right, but the punchline is the same. A vector differential is a notation that encapsulates both size and orientation, and is a convenient thing to write just kind of on its own, again, for sort of compactness and sort of notational naturality. So the analogy is actually pretty strong there. Y'all willing to buy it? I use this notation a lot, this f dot ds vector notation. I think it's extremely natural. I'll be using quite a bit. Okay, so let's see here. So let's talk about terminology. This happens over a surface, thus the name surface integral. And you can probably see now why we distinguish this as a vector surface integral, because the differential is a vector and the integrand, viewed what I think is most naturally, is also a vector. And thus the term. All right, so vector surface integrals. By the way, let's just count real quick how many different kinds of integrals we've seen. Single variable integrals, double integrals, triple integrals, scalar line integrals, vector line integrals, coordinate line integrals, which are arguably just kind of a notational thing, but they are, in fact, a different kind of integral you can write down. Anyway, that's questionable whether we include that. Then, as of Monday, we had scalar surface integrals, and as of now, we also have vector surface integrals. So we've now defined 8, at least 7, depending on how you count, but arguably 8 different kinds of integrals, and there's one more coming up soon. You might be able to guess what that might be. Not a big deal, but we'll get to that in a few. But lots of different kinds of integrals. All right. Good news, we already know how to compute these. Everything we need to compute these is pretty much already set up. There's one quick little connection to streamline the process I'm going to throw out there. But all of this is old news. We've already talked about how parameterizations make this normal vector whose magnitude is a stretching factor between input area and output area. I mean, that's, again, flashbacks. Yeah. So all we have to do is take the formulas that we just wrote down. Just wrote these down. I'm going to look at this one specifically. I'm going to substitute the formula that we just talked about. That formula right there. No big deal, right? I'm just plugging stuff in and just kind of moving things around. And then, hey, let's think about this thing. We have a unit vector pointing in the normal direction multiplied by the magnitude of this capital N in the normal direction. And isn't that kind of a direction and a magnitude? Isn't that what a vector is? In fact, isn't that what capital N is in the first place? And I think we even wrote that down at some point in the past. Now, you will have noticed I put an asterisk over here. I did just commit a little math crime. I'm going to come back and confess that later. But 2 things. I want to be dramatic about it. So it helps students, I hope, to remember if I'm dramatic about the mistake that I just made and the reveal that will come later. I want you to see how easy it is to accidentally oops this. So I'm deliberately accidentally oopsing this. And also, I just kind of want to get one in the win column. Let's do a computation. Let's see how these work. Let's actually compute, and then we'll talk about the kind of subtle problem that I just introduced. Okay. All righty. So if you want to compute a flux, pick your favorite notation. Compute with this formula, which of course simply requires that you parameterize your surface, compute the capital N, and plug and chug. Okay, so off we go. All right, here is a flux calculation, and we want to compute the flux of this vector field over that surface. Following the prescription we just discussed, first thing we need to do is parameterize the surface. Let's see here, z equals x squared plus y squared. Ooh, it's a graph. I'm going to use the graph parameterization. Make sure you can do that. Again, we talked about that on Friday, I think it was. Super duper useful parameterization tool. We're going to be doing it a lot. Anyway, there it is. You take various partial derivatives. Make sure you can do that, of course. You cross to get the capital N vector. Make sure you can do that, of course. And then it's largely just a matter of plugging in. Let's see here. We've got the capital N we just computed, capital N. is that. A little bit of a tricky bit with the vector field. The vector field, okay, our formula for the vector field is this. Why did I write down this? And the reason why is you got to remember you've got to do the pullback. You have to plug in for what x, y, and z are. And in fact, the parameterization is what tells you what x, y, and z are. And specifically, x, y, and z are like that. And so let's see here. This x is thereby s, because that's what that says, right? And et cetera, et cetera. And then, of course, z is s squared plus t squared, so that's why that is s squared plus t squared, and et cetera. Everybody okay? I mean, again, it's just kind of plugging into the formulas we've established, and these kinds of questions, when you do a straight parameterize and plug and chug computation of a flux, it's very pluggy chuggy. Okay. All right. So let's, as we have in the past, let's think about the question of, does the choice of the parameterization matter? And let me remind you, we've entertained this question several times previously, right? When we were talking about scalar line integrals, does the parameterization matter? And the answer was no, it doesn't matter at all. Knock yourself out, go crazy. Whatever's your favorite, whatever's the most convenient parameterization, fine. When we were talking about vector line integrals, it started to matter a little bit. When you parameterize a curve to do a vector line integral, you've got to go the correct direction. You can't go backwards, right? That messes things up. That introduces a minus sign. So as long as you don't parameterize backwards, doesn't matter. If you do parameterize backwards, okay, confess, put in the minus sign to correct for it, citing a theorem from the notes, and you're easily dealt with. Right? But you have to worry about whether you parameterize the right way or the wrong way. So here we are again. Does the parameterization matter? And yeah, again, it does matter a little bit. You have to worry about whether you parameterize the right way. So let's remind ourselves of the deal. If you are looking at a flux through some surface, again, it can't just be a random surface. It has to be an oriented surface. Flux only makes sense if there's an established, agreed upon direction of what you consider to be the positive direction, and we indicate that by way of what we call the orientation unit normal. Now, you're free to orient a surface however you like if it's not already imposed on you by the statement of question or something about the context. Don't forget the word boundary always is a loaded word. Boundary always means that there is an implied orientation. We'll talk about that later. But if you're going to do a flux, your surface has to be oriented. And then here's the thing. We decide we're going to do this by parameterizing. So we create a parameterization. When we write down that parameterization, do we think about orientation? Did I think about orientation back here? No. I saw this equation for this surface. I wrote down the graph parameterization. I wasn't thinking about orientation at all. I pulled this parameterization. As far as orientations go, I pulled this parameterization out of a hat. Right? No recognition in that process of the fact, it says right here, my surface needs to be oriented upward. I blew that off entirely. So this, in fact, tends to be the way stuff works. When you write down a parameterization, you write it down with other interests in mind. And, of course, that's going to imply partial vectors. It's going to, therefore, imply a capital N vector, which will imply what we've called the parameterized unit normal. And it is a coin flip as to whether you parameterized the right way or the wrong way, depending on what the orientation of the surface is. Did everybody see the problem? All right. Okay, so Not that different, really, from what we saw with vector line integrals, where, there's 2 ways to parameterize, and you just got to make sure to parameterize the correct direction. Okay, now, this is the mistake that I made, my little math crime, right? I wrote down that was equal to this, but importantly, let's see, let me get the colors consistent. This one came from the surface itself. When I claim that capital N is a direction and a magnitude, yeah, okay, true, but capital N is a direction and a magnitude where the direction comes from the parameterization. So I equated this expression to that expression in claiming what I concluded in purple here were the same thing, and they're not necessarily the same thing. I was conflating the orientation unit normal with the parameterized unit normal, and no fair. So that's the sloppiness. Everybody see the mistake? It's very subtle. Okay, so bad news, good news. Bad news is that this is something you have to worry about, and you have to get it right, and it's important. And this is ultimately just a minus sign, but it's an important minus sign. It's a minus sign that is representative of a sophisticated and meaningful and important part of what we're learning in this course. And so, again, I've made this statement before. Orientations tend to matter pretty significantly. On a 20-point question, it might be 4, maybe even 5 points out of a 20-point question. So you really want to take orientation seriously. You have to think it through. And just reminder, when we wrote down, let's see, at some point we would have been tempted. Let's see, let me go back to it. Here we would have been tempted to say ds is capital N ds dt. Sure looks like it. But again, this apparent result is involves my sloppiness that I've just confessed to. So in fact, there is a plus or minus issue, and this plus or minus issue I'm going to recognize by putting that in there. And good news, it's just a minus sign. Right, bad news, you got to be careful. Good news is it's easily fixed. If it turns out that for whatever reason it's easier to parameterize upside down, or said differently, if you parameterize just trying to get a parameterization on the page, and then you subsequently realize that you parameterized upside down, no sweat, fix it with a minus sign. And I'll show you an example in just a moment. Okay, one last little bit of good news. Other than this minus sign issue, parameterizations don't matter. So, in fact, day in and day out, parameterize however you want, and worry about the orientations afterwards. Okay, so here's an example. We're going to look at, let's see here, I'm going to do that like this. We want to compute a flux of this vector field through a portion of that surface, specifically above the unit square. In fact, this is practically the exact same example we did previously. Same vector field, same surface, same part of that surface. The only thing that's different is that here you see I'm orienting the surface downward. Right? Downward oriented portion of that surface. How are we going to deal with the orientation on this? So again, don't worry about it. Step 1, don't worry about it. Parameterize however is most convenient. Graph parameterization is hard to beat. Compute your partials, compute your cross product, et cetera, et cetera. And then pause. Look at your capital N vector that you just computed. You have to, by the way, it's on you to remember that you have to do this, right? You have to pause at this point in the calculation, and you have to ask yourself, wait a minute, did I, when I wrote down this parameterization here, did I parameterize it the right way or the wrong way? And how do I tell here? The way you're going to tell is think about what the orientation says here. It says downward there, but you can see that this capital N vector that I just computed is not downward in any sense. It's not even a little bit downward. It's, if anything, upward, right? It's not straight up, not perfectly up, but it's... No one's going to look at a vector like this, like I'm doing with my finger here, and call that downward. It's just not. Does that make sense? So I parameterized it backwards. Okay, do I need to redo the parameterization, hoping that I will get it right next time? No. Don't redo the parameterization. Just recognize that you parameterized the wrong way. Right, let's see here. I will point out that we did not parameterize correctly. And I'm going to fix it by just inserting an appropriate minus sign in the calculation. That's all there is to it. Just, admit that you did it the wrong way. Whoopsie doodle, right? I parameterized upside down. Stick in your minus sign and keep on going. It's very convenient, actually. It's not that big a deal if you understand the geometries, the ideas of the geometry of, what's an orientation, what does it mean, and how does it relate, stuff like that. It's very easy to actually deal with. Now, I will point out, and this is an underappreciated issue, but it does matter where you insert your minus sign. It matters a lot. I want to remind you, I know I say it a lot, but I say it a lot because it's really important. This is not a class about answers. This is a class about ideas. Right? Ideas and reasoning. And you have to give me legitimate reasoning. And if your reasoning is not legitimate, right, well, it's going to, that matters. Right? That affects our evaluation of your work. Right? So where you put the minus sign matters because you have to put the minus sign where you're making the switch from stuff that depends on the given orientation to stuff that depends on the parameterization that you pulled out of thin air, right? And this is where we made that switch. This ds vector has a normal direction that comes from the given orientation. ds is intrinsic to the surface. Capital N ds dt. Well, this capital N comes from the parameterization. It's never heard of the given orientation of the surface, right? So this is where we're making that switch. This is where, therefore, the fact that we got it wrong matters. So this is where you have to insert that minus sign. Okay, you absolutely cannot do the following. Here's what a lot of students will do, and just not okay. A lot of students will not put it there or there. Will continue doing their calculation. And then we'll get some answer, some value, and then we'll say equals minus a. And let's just take a moment to recognize the volume of garbage that we have here, right? That's just not acceptable in a math class. You can't write down a equals negative a. You can't do that. That's not okay. Right? I mean, right? You can't. That's garbage. If you're interested in reasoning, not answers, that's unacceptable. Make double sure you don't do that. Just not okay. There's another error here, which is in saying that these are equal. No, they are not. Right? Not only are those not equal to each other, these are not equal to each other. ds is not capital N ds dt in this context. That ignores the fact that we parameterized upside down and that capital N is pointing the wrong direction. They're not the same. Right? So if you're careless about how you insert your minus sign, you will create multiple false statements in your reasoning, and mathematicians are pretty uptight about that. Everybody can see what I'm talking about here? Okay. All right. So please be careful about that. It does matter. It will count in the grading. All right. Okay, now I want to address sloppiness of the language. We do speak kind of casually when we talk about orientations. You'll notice here I said we're looking at this a portion of this surface which is not a horizontal surface, right? It's curved, it's very curved, and yet I described the orientation as downward. The orientation is not perfectly exactly straight downward. So, how is that okay? How can we get away with that? The big realization on this point is that when we talk about orientations, we are trying to distinguish between two possibilities. We are not trying to be precise. We're just trying to be unambiguous. Right? So let's look at, for example, a paraboloid like we were just looking at. Here's a kind of a paraboloid. The two different orientations, right? It is possible, you could orient this, what I'll call, well, let me not call it anything. You could orient as per the green vectors, or you could orient as per these blue vectors. And let's talk about how we would distinguish between these two. Do I have to write down an explicit formula for the green or the blue just to make sure that I communicate unambiguously which one I'm talking about? No, I claim you don't, because the green one is the only one that is in any sense upward. It's not perfectly exactly upward, but it is somewhat upward. The blue one is never anywhere, even slightly in any sense, upward. If I say upward, no one should be confused as to which one of those orientations we're talking about, right? We're clearly talking about the green one, not the blue one. And likewise, downward. If I say downward, no confusion. The blue orientation is always at least a little bit downward. The green orientation is never, in any sense, downward, unambiguous. So it's not precise, but it does the job, right? The job when you describe an orientation is just to unambiguously distinguish between the two options. So this is perfectly fine, and that's how people describe these things. Okay. Do be careful with alternatives. Some people would say inward versus outward. Case could be made that the green one maybe is kind of sort of inward, and the blue one is kind of sort of outward in some sense. My quibble, see, I have a little bit of a quibble on this. I mean, it's not wrong, but it makes me uncomfortable because there is no inside. This surface is not closed. There is no actual inside. So inward, in this case, doesn't really mean anything. If you get a quibbly grader, conceivably they might complain about something like that. So you want to try to avoid language that doesn't do the job, right, of being unambiguous. Now, on the other hand, if you're talking about a sphere where your two possible orientations are like this, notice upward versus downward doesn't cut it. Right? Upward versus downward doesn't make any sense at all. The green orientation is upward in some places. The blue orientation is upward in some places. Not helpful. Not unambiguous. Right? But in this case, inward versus outward, perfect. There is an inside. This is a closed surface. So the blue one is inward, the green one is outward. Everybody kind of see what I'm talking about? Okay. All right. So something to keep your eyes on. Okay. Yeah, so sometimes you get lucky. Heads up. Right? Always keep your eyes open for the possibility that you might save yourself loads of trouble. So here's one, and we have compute the flux. By the way, notice in the statement of this question, nowhere does it say. By the way, there's a super cool geometric convenience here that's going to save you loads of trouble. It's not in the statement of the question. And this is intended to be representative of how you're going to have this experience when you're doing engineering or physics or whatever it is that you're going to be doing. These circumstances will not announce themselves, right? And so you have to be on the lookout for them, and I want to encourage y'all to, just always head on a swivel, always. Anytime I compute a flux, one of the very first things I do is I look at the situation and I ask, is there any geometric convenience here that might make things super, super convenient? And if so, is it actually going to, am I going to be able to capitalize on that and save myself some trouble? And it's usually a pretty quick glance. So here we have this sphere. Spheres have fantastic symmetries. It says right here, oriented outward. So I know my orientation unit normal is outward. I also know that the position vector on the sphere, if I look at that point where I'm evaluating that normal, look at that position vector. Again, you got to love spheres. One of their many wonderful symmetries is that the normal vector is parallel to the position vector. It's awesome geometry for spheres, right? So something to keep a lookout for. Because of that, because they're parallel, the one is a multiple of the other. Not hard to see that the position vector has magnitude 3. It says so right here. The radius is 3, and this is a radius. So to get a unit vector pointing in the same direction, I just divide by that magnitude. And we have here now, notice no parameterization. I haven't done any parameterization. Right? And yet I have a foot in the door for how to deal with this orientation unit normal vector. My orientation unit normal vector is just xyz all over 3. Now, do we score? Does this actually help us? Sometimes it is, sometimes it isn't. Now, in this case, we can look at our vector field, right? The thing that we're doing the flux of. We put that in there like this, and you just have to multiply it out and see. And in this case, turns out it doesn't leap off the page at you. But when you dot this up and add up the terms, yep, 0. Integrand is 0, so the integral is 0. And we never had to parameterize anything. I never had to worry about, oh no, did I parameterize right side up or upside down? There is no parameterization to create a possible confusion. Everybody happy? Again, came up a lot in my undergraduate years. I think it'll come up significantly for y'all. Definitely worth keeping an eye out for. Big trouble saver. Here's another example. Different kind of geometric convenience. Planes have wonderful symmetries. And here's the plane in question. We're going to look at the plane, part of this plane, y equals 3. That's a plane that looks like this. And there's a couple of ways that this ends up being awesome. First way that this is awesome, I can write down the normal vector super easily. There it is. Oriented correctly anyway, oriented in the positive y direction, cool, positive y direction. So, sweet. Right, and so I'm just going to pop that in for my orientation unit normal right there. And is this one observation alone enough to make everything go away? Well, no, there is the vector field. I do have to deal with the vector field. But the second bit of awesomeness is that because I'm on this plane y equals 3, I can plug that in for y. Because after all, the only reason I care about this vector field is because it's on my surface. My surface is entirely in the plane where y is literally 3. So I can plug in y equals 3. That makes this term 0. which goes there. And that makes things easier yet again. Two observations out of the same little convenience, right? The fact that we're on this plane helps us out twice, two different ways. And then now is when we celebrate, we make the observation that, oh, there's a bunch of other stuff going on here. You know, the first coordinate of the vector field, the third coordinate. Oh my gosh, there's a coordinate describing exactly which part of this surface, right? Lots of other stuff going on. And yet, the dot product, obviously 0. We drop the pen, we walk away. We didn't have to deal with any of that ugliness. What do you think? Is everybody happy? And again, something to keep an eye out for. You know, will this always work? Definitely not. Yes.
Could you, when you're rewriting that at the end, the last dot product?
Yep.
Would you, like theoretically, could you plug in 3 for y?
Oh yeah, for sure. Yeah. No doubt. I could totally. Yeah, I can put the 3 there. And I guess that's the only one. Yeah. So yes, absolutely. The only reason I didn't is because I could tell it wasn't going to matter anyway, and I just I felt like it would be visually easier to see how I just recopied this and put it there. But yeah, totally, absolutely. Okay, so keep your eyes open, right? Planes, this is pretty convenient. This kind of stuff comes up for planes. And spheres, this kind of stuff comes up for spheres. Okay, now y'all remember the business about coordinate line integrals. Something analogous happens for coordinate surface integrals. I want to be pretty quick with this. Here's our formula that we wrote down for the ds vector, relating ds to the parameterizations. Don't forget the little plus minus. By the way, I put the plus minus in here because I wanted to leave open the possibility that we might parameterize upside down, and I don't want to impose on us that well, you have to parameterize right side up, that you have to parameterize the correct direction. Because I don't, in practice, day in and day out, that's just not that's not how stuff tends to go down, right? So that's in there to give us that additional freedom. I'll point out that there are some contexts in which the assumption is that you must parameterize the correct direction. And if it's assumed that you must parameterize the correct direction, then you don't need this plus minus. And that just disappears. And so if when you find it in textbooks that there is no plus minus in there, that's why. And it's, you just, that just means that it's then on you, unprompted, to remember, okay, this only works if I parameterize the correct direction. Right? And you have to do that. I like this better. Well, anyway, so we have previously discussed capital N being this cross product. I previously noted that you can write that out in coordinates, and I previously noted that when you crank out that cross product, the coordinates are mysteriously, they're little two-dimensional change of variables stretching factor determinants, like so. And isn't that weird? And it is kind of weird. So notice that what we have then is a situation where we can take the, let me not get the colors too wrong here. I can kind of distribute the ds dt, and then pretty natural to ask the question, what should I call that thing? And I mean, the whole reason we like this fraction-like notation in the first place is because when we were doing change of variables, we multiplied by ds dt. It's nice to be able to, again, that you can't really get, it's not actually a cancellation, but it's as if, and it always works, and you always get the right answer. We cross these out, and we call this, dy dz. So likewise for the other coordinates, and nice punchline then, we have a coordinate notation for our ds vector. This is totally analogous to what we did with line integrals. And we can take that and plug it in, let's see here, ds being that, this becomes that. Don't forget your plus minus. And if your vector field is PQR, then notice again we get a dot product that you can expand, and we have here a new alternative notation for vector surface integrals. I'm going to call these coordinate surface integrals. This is an alternative notation for that. Very analogous to the line integral sort of a version of this, and very analogous in terms of why am I telling you this, and what's the upshot for us in Math 219, and what's the upshot for y'all after you leave Math 219. All the same stuff. This is culturally a pretty important thing to be aware of. There are excellent reasons to like this notation. This is not quite exactly what it looks like when we talk about integrals and differential forms, but it's pretty close. It's highly suggestive of integrals of differential two forms, we call it. It's kind of, again, good to just know what's out there, be aware of the big picture of things, so that's a good thing. More importantly, though, this is something that you're going to see. Right? People like this notation, and so you're going to see when people use this notation. So you have to be heads up. You have to be on the lookout for stuff like this. And when you see this, you have to know what to do with it. Right? And in particular, the same story that I gave y'all with coordinate line integrals. When you see something like this, my idea is just remember that this here is just an alternative notation for the ds vector. And therefore, this P, this Q, and this R, you can use that to interpret it appropriately to sort of reverse engineer what your vector field is that you're computing a flux of. Right? Anytime you see something that looks like this, work it backwards, reinterpret like this. Everybody okay with that? So for our purposes in this class, this is just mostly just a notation to be, reinterpreted in a more convenient way. Okay. All righty. Okay, let's see. Let's just do a little bit more here. Symmetry theorem. So, this is a pretty quick conversation. This is perfect. We've been down this road for symmetry theorems several times. I hope it comes as no surprise that we have a theorem and a collection of warnings that are morally equivalent to what we've seen for single variable integrals, double integrals, triple integrals, scalar line integrals, and now scalar surface integrals. And so if you have a symmetric domain and a odd integrand, by the way, both of these conditions have to hold, and it's got to be the same plane for both of them. Then integrals equal to 0, walk away. Right? And again, you do have to make the case, right? You do have to demonstrate. Remember the 5 conditions we talked about. You got to, give us what we need, right? But same basic ideas. I hope that's believable. And same warning, same related landmine. This only works for scalar surface integrals. For vector surface integrals, it does not work. Straight up does not do it. There is no odd symmetry theorem for vector surface integrals. And for pretty similar reasons. You write down your vector surface integral, write it in this way here just for convenience of getting at what we need. And think about this orientation unit normal. And notice that this orientation unit normal just does not behave very nicely. When you're looking at a symmetric surface, symmetric through a plane, symmetric pieces, they have the same area. The vector field at these points, these points are reflections, and so that vector field is, at these 2 different points is going to behave in a very nice and predictable way. But these normal vectors, they're not the same. They're not negatives of each other. They're just different. And so crash and burn, no theorem. Please be very, very careful about this. Please do not try to use odd symmetry for vector surface integrals or vector line integrals. Drawing the line right here, picking up here Friday. See y'all later. Have a good one. Don't forget about attendance.